Hey everyone, today I'm going to be showing you transparent metal. I've done a lot of experiments with sodium in the past, but we've usually focused on it exploding when you put it in water. But today I want to show you what happens when it doesn't explode. It actually turns completely transparent. Watch this. Okay, here's our chunk of sodium. I'm just going to drop it on this filter paper in water. 3, 2, 1. Whoa. It's completely clear now. Look at that. Whoa. So we actually end up with a crystal clear drop here that suddenly explodes at the end. So why are metals normally opaque anyways? Well, it has to do with the same reason why metals are good conductors. It's because they have free electrons. The valence electrons in atoms are free to move through the entire piece of the metal. They're not bound to the atoms. This means that they move around in the piece of metal just like particles of a gas. So you can treat these electrons like an electron plasma. And there's actually a relatively simple formula for calculating the plasma resonant frequency, it's called, for free electrons. This formula tells us that for low photon energies like radio waves and microwaves, for example, the free electron plasma is almost a perfect reflector. But for mid-range energies like visible light, this is right close to the plasma resonant frequency, so it absorbs the light. But then for higher energies than visible light, the electron plasma becomes transparent. Now for real metals, this isn't exactly true because the electrons can jump into different orbitals and change the plasma resonance frequency slightly. This makes it so that you can have colored metals like gold that absorb blue and green light and reflect yellow light. But in general, all the metals act nearly the same in terms of light absorption because they all have similar electron plasmas. So you never see any transparent metals in the visible range. But what about what we just saw? Didn't the sodium turn transparent? Well, let's look at the reaction in more detail. When you put sodium in water, the sodium has such a weakly bound outer electron that the electron will attach to the free protons in the water to create hydrogen gas. This leaves you with sodium hydroxide salt, which is transparent. And since the sodium hydroxide is so hot, it's actually in its molten state, so you end up with a molten drop of this alkali metal hydroxide. So the reason for the filter paper on top here was just to slow the sodium reaction down with the water, so it doesn't all happen at once. So the ions are able to transport across the filter paper and react with the sodium. So overall, you're left with a molten ball of sodium hydroxide. Whoa, it's completely clear. Now, one thing to be aware of in this reaction is normally sodium metal is lighter than water, so it floats on top. But in this case, even if you put the filter paper on top, once the transfer is complete and it's completely sodium hydroxide, it can melt down through that paper, so it burns down through the paper and drops down below into the water below it. So the Coulomb explosion that happens once it's down in the water is a lot bigger. So this is how it happened when I tried it with a glass beaker first. The drop just fell down into the water and exploded my beaker. Oh. Whoa. So the reason that it becomes transparent is because it actually isn't a true metal anymore. It's a metal hydroxide. Even these other metals that you might have heard of in the news, like transparent aluminum, isn't actually a true metal either. It's actually aluminum oxide. So it seems we're out of luck if we want to see a true transparent metal. But maybe not. In the visible range, the electron plasma has a large extinction coefficient, which means it absorbs light strongly. But when something absorbs light, it doesn't just instantly absorb all the light that hits it. The amount of light that penetrates into the metal actually decays exponentially. This means that for very, very thin pieces of metal, there can be significant amounts of light that gets through. But it has to be really thin. So I have here a piece of aluminum that's only about 100 nanometers thick. The reason I'm able to hold it so easily is because it's attached to a piece of plastic. The way it was made is by vacuum deposition, where the metal evaporates and then condenses onto the plastic. So you can see a really good reflection here because in this range, most visible light is reflected, but some is also absorbed. That's why the reflection looks gray, because the reflected light coming off is dimmer than the light that hits it. But also, since the metal is so thin on here, some of the light is actually transmitted as well. So there's some light getting through. But let's see what happens when I shine my green laser from the back here. You can totally see through it. So this really is a transparent metal. So when you have metals in the range of nanometers, then the metal's no longer completely opaque. So it looks like this is being 100% reflective, but it's not actually. Some of the light is actually getting through. It's so weird to see the laser go through with this shiny metal here. And thanks for watching another episode of the Action Lab. With the Christmas season coming up, if you're looking for a good science-themed gift, you can head to theactionlab.com, where we have experiment boxes for sale, and also we sell a cool painting my wife painted of an astronaut falling into a black hole. And the black hole portion is actually hand-painted on every print with Musso Black, the world's blackest paint. So it gives you a really cool look in the end. And thanks for watching, and we'll see you next time.